Okay, we're back, and we're doing some modern physics, and in particular, here's the probably, in my opinion, the single most famous equation ever written down. If you ask people on the street to name an equation, they can probably recite E equals mc squared. Likely have no idea what it means, but they can state it. So where did it come from? Where did Einstein get the ideas? How can we think of a derivation for this? Well, it's a little more complicated than what we'll show here, but this is a pretty good way of thinking about it. And in particular, we're taking one of the equations that he derived from relativity, this mass equation down here. Okay, this equation allows you to figure out, for a given speed, how much the mass of a moving object will be at that particular speed. This m sub 0 on top is the rest mass, and you're solving for the mass on the left, which is the new mass at the particular speed. So there's that square root in there, and I just rewrote it here on the right-hand side as this quantity that you see all the time in relativity, 1 minus v squared over c squared, where c is the speed of light. Okay, that's a constant 3 times 10 to the 8th meters per second, the fastest speed in the universe, as far as we know. And I'll write that in terms of this negative power. It's 1 over the square root of that quantity. Now, the way I'm going to approach this is to think about an approximation. Think about everyday speeds. Okay, think about a car moving at 30 miles an hour, or you walking, or a plane flying at a few hundred miles per hour, whatever, just everyday speeds. Obviously, that's a whole lot slower than light. So we're in this limit here that I just circled, where your speed, the v, is a whole lot smaller than c. When you square these numbers, that means that v squared is a whole lot smaller than c squared. And what's more, that means that this fraction that we see in the square root, this v squared over c squared, is a really tiny number, so it's much smaller than 1. Under these conditions, we can do what's called binomial approximation. We can expand the square root, which I'm going to circle here in red. We're going to think of it in this form here with this negative 1/2 power. The reason for that is this binomial approximation, something that some people may have seen this in like an Algebra 2 class or calculus or something like that. But if you haven't, here's the gist of it. For any quantity of this form, the quantity 1 minus x to the nth power, if x is much smaller than 1, and n can be anything. N can be an integer, it can be a positive number, a negative number, it can be a fraction. It's just some number that some power that you're raising this quantity to. But if x is much smaller than 1, then we can approximate the value of this quantity with this expansion. Okay, 1 minus n times x, then minus n times n, the quantity n minus 1 over 2 factorial times x squared minus blah blah blah. You can keep adding terms on as far as you want to go. Well, for us, we're going to compare this to the quantity in Einstein's mass equation. We're going to look at the quantity 1 minus v squared over c squared to the negative 1/2 under the condition that v squared over c squared is much less than 1. Okay, so we're in everyday speeds. And let's see what this binomial approximation tells us. We're going to have 1. Now our n value is the negative 1/2, so we're going to bring negative 1/2 times x. Well, the x is v squared over c squared. Now we're going to have negative 1/2. N minus 1 is a negative 3/2. That's all 2 factorial. Then we're going to have v squared over c squared squared. And then you could keep doing this all day if you wanted to. But it's not going to do you much good. The reason is, you can change colors again. Think about these v squareds over c squares. Now, by itself, that's a really small number. When you square it, that's a really, really small number. If you were to cube it, that's even much smaller. So at some point, these are such small numbers that they don't really matter. So I'm basically going to scratch the second order term all the way down. We don't care about those because they're too tiny. They're so far down in your decimal places that you don't care. And we're just going to keep these first two terms as our approximation. Now let's put it back into this mass equation. Let's see what this approximation does. So we're saying that our new mass is the rest mass times this funny quantity here. And this is approximately going to be our rest mass times 1. Now we have minus minus, so it's actually going to be plus a half times v squared over c squared. Okay, I just brought that right down from our approximation, this expansion. Okay, so our new mass is approximately, now let's multiply this out. Our rest mass plus 1/2 rest mass times v squared over c squared. I don't like fractions, so let's multiply everything, all three terms here, by c squared. Let's get rid of that fraction. So on the left-hand side, check out what we have. Our total mass times c squared. Okay, it's approximately, I'll just put the equal sign in there. Our rest mass times the speed of light squared. And then 1/2 rest mass times your speed squared. Okay? This is what we end up with. Now, on the right-hand side, this 1/2 mv squared, that's just our normal classical kinetic energy. This term, the first term on the right, the rest mass times the speed of light squared, it has units of energy. It's kind of like a potential energy. It's the stored energy. It's the energy of the matter itself of the object when it's just sitting there. Now, what do you normally get if you have kind of like a stored energy or a potential energy plus kinetic energy? Well, that typically in classical physics tells you what your total energy is. So that's where we can get this idea that your total energy is mc squared. Okay, now Einstein did a whole lot more at this, but I'm just going to keep it here for now just to give you an idea of one way of thinking about this, where the notion of equivalency squared comes from in the first place. Now remember, this is an approximation, what I showed here. This is for everyday speeds. There's a more general way of doing this without approximations for all speeds. And that I'll save for the other video on special relativity. But for now, you know, this is just where it comes from. This is one way to get Einstein's, one of his most remarkable discoveries, that energy and mass are related to each other. And not just related, it's an equal sign. We're talking about the equivalence of matter and energy. They're two forms of the same stuff. You can convert them and change them into each other. This led to nuclear power, atomic weapons. It allows us to understand nuclear science. It allows us to understand how stars work and how they burn. It's one of the great discoveries of the 20th century and of all time. So hopefully this makes a little sense. It started with one of his results from special relativity. We made use of the binomial approximation, and we ended up with an idea of that energy and mass and matter are equivalent to each other. So I hope this helps. Hope you find it interesting. Until next time, we'll see you later.